So just a quick outline of what I'm going to talk about here. I'm going to start off talking about the volatiles that are present in the Earth's mantle today. Not all the volatiles are on the surface, and so I want to talk about how much there is and the effect that they have on the rheology of the mantle. And then I'll talk about atmosphere-magma ocean interaction. So this is the magma ocean stage that Robin Wordsworth was talking about yesterday, which is very common in the beginning of planet formation. And then I'll talk a little bit about deep volatile cycles. This is after the magma ocean has solidified and how volatiles are flowing between the atmosphere and the mantle over very long time scales. And at the end, I'm going to talk a little bit about the carbonate-silicate cycle. But for the most part in this talk, I'm going to be focusing on water because there's a lot of information about volatiles and how they interact with silicates. And so I'm just going to focus on water for now. So I'm going to start talking about how much water is there in the mantle. We know there has to be a fair amount to support the jungles and dinosaurs that we know are down there. But exactly how much is that? So the water in the mantle is found in what we call nominally anhydrous minerals. So it's not really in hydrated silicates. It's more found in minerals that don't have water in their chemical structure. So olivine, for instance, is a very common upper mantle mineral. It's Mg2SiO4, for those of you who don't know what olivine is. And you can see that the amount of water that you can put into olivine increases as a function of depth or pressure within the planet's mantle. This figure over on the left is showing the water storage capacity of the Earth's mantle. Sorry about the microphone. So you can see that the water abundance is increasing in the upper mantle because olivine is one of the dominant minerals up here. And then we have this transition zone. So there are some higher pressure phases of olivine that seem to have a very high capacity to store water. And so there's two of them, ringwoodite and wattsleyite. Now, I just had a brain fart there. And in the lower mantle, the dominant mineral is bridgemanite, which seems to not be able to store a lot of water. And so we think that this is a much drier region of the mantle. And then down here, there might be a little bit of post-perovskite, which from lab measurements and ab initio calculations seem to have a slightly higher water storage capacity. And then down here, there is also hydrogen shown in the core. So this wouldn't be water necessarily, but hydrogen. And we have really no idea how much hydrogen there could be in the core. It's very unconstrained. For the total amount of water in the mantle, here's a couple of recent references where people have tried to assemble information on basically on the silicate sources within the mantle. So these are looking at how much of the mantle is going into the sources that are making mid-ocean ridge basalts or ocean island basalts like Hawaii and Iceland. And using the abundances of those materials, so the ocean island basalts are probing sort of the lower mantle, whereas the mid-ocean ridge basalts are probing the upper mantle. And you can look at those kinds of fluxes and try to get an estimate of the overall abundance of water in the mantle. And so they're ranging from about 0.2 up to 1.5 times the amount of water that is on the surface. So this is an ocean mass that's total water on the surface, and there's at least 1 time that in the mantle. This reference from Marty is looking at sort of cosmochemical estimates of how much water there might be in the mantle, and he gets something like 10 plus or minus 5. So this is significantly more. And so you can see there's a huge uncertainty in the amount of water that's in the mantle. Now the water in the mantle affects the rheology, or the material properties of the silicates, in two really important ways. The first is the depression of the melting point of the silicates, which is shown in this figure on the left. So what's shown here is the melting point of this is peridotite, as a function of pressure and temperature. And as we add water to the system, the melting point decreases. This sort of purplish line is a perfectly saturated melt. So this is the lowest temperature that that could be achieved in this system. Water also affects the viscosity of the silicate. This is the viscosity of dry olivine compared to olivine that contains about 1,000 parts per million. So you can see that at 1500 Kelvin, this is a factor of, 4 orders of magnitude decrease in the olivine viscosity. So that can have a significant influence on the rate of mantle convection and therefore the rate of exchange of material between the mantle and the surface. So I want to jump now and start talking a little bit about how the atmosphere and the interior are interacting in the very earliest stages of planet formation. And this is when we have magma oceans. So we think of magma ocean as a fairly common stage for terrestrial planets, particularly after giant impacts. So this is a cartoon schematic of how a magma ocean is solidifying, which is shown much more diagrammatically over here. So what we're seeing here is, again, the solidus of the silicate mantle and the liquidus. So this is the region in here where the mantle is partially molten. So you can see there's solid in liquid or liquid in solid, depending on whether you're closer to the solidus or the liquidus. The mantle is convecting during the magma ocean stage, and so it's following an adiabatic temperature gradient. And you can see that the adiabat is first intersecting the melting points at the bottom of the mantle. So this is where we get solidification of the mantle proceeding from the bottom towards the surface. So the surface will stay liquid for longer than the deeper interior. And what's happening in this is we have volatiles like water or CO2 are dissolved in the silicate liquid. And they will partition partially into the solid, but they prefer to stay in the liquid phase. So as the magma ocean evolves, the silicate liquid is going to become enriched in the water, and that's going to also affect the atmospheric pressure. This is the solubility of water in different kinds of silicate melts. Down here we have the water abundance in the melt, and this is the pressure, the atmospheric pressure that would be in equilibrium with that melt. This is the solubility element written here. So you can see that we have we have 2 melts here, a basalt and a rhyolite, and this Henrian. This is just an idealized model for the solubility. So you can see that as we increase the water abundance in the melt, we are going to increase the atmospheric pressure of the magma ocean. Of the atmosphere that is in equilibrium with this magma ocean. And we can derive similar solubility limits for other volatiles like CO2. There are also measurements of the speciation of volatiles within the silicate melt. This is a figure from Armstrong et al. 2015, looking at, this is the abundance of water in the melt. And this is showing that the speciation of the volatiles in the melt are a function of the oxygen fugacity. So this is the redox state that Robin was talking about yesterday. And it's a little confusing here, but you can see that at low oxygen fugacity, so this is a very reduced system over here and oxidized over here, that carbon in the melt will be in the form of methane. And as we go to more oxidizing systems, it will either become CO or carbonate. Hydrogen is found in H2, but over here we can see that this is also a function of redox state. So this is the amount of hydrogen in the magma, and this is the fraction of hydrogen in the melt that is in the form of H2 relative to H2O. Okay, so that at very low redox states and high hydrogen abundances, most of the hydrogen in the melt will be in the form of H2, whereas at more oxidizing conditions, most of the hydrogen will be in the form of H2O in the melt. So this will affect the degassing of these melts and also the overall solubility of materials in the silicates. Here's an example of a magma ocean evolution calculation. So what we do here, and this is work that I did with Robin, her paper on GJ 1132b. So we do a thermal evolution model. So this is sort of a 1D model for the magma ocean, where we're tracking the temperature of both the interior of the planet, that's TP, and the surface temperature of the planet. And then we're also tracking the distribution of hydrogen between 3 different reservoirs: the solid mantle, the magma ocean, and the atmosphere. And the volatile cycle is shown in these equations over here. So you can see that we start off at a very high temperature, and for a while the interior and the surface temperature are basically the same. And then we get this break here where the surface temperature is this dashed line, the mantle temperature is now diverging. And what's happening here is that the interior is now in sort of a mush stage, where most of there's a lot of crystals suspended within the melt. And so we get the development of a boundary layer that is sufficient to allow separate cooling of the surface and the interior. And so at this point, we can basically say that the magma ocean stage has ended, and there is no longer direct interaction between the atmosphere and the melt. Now we actually have to have an eruption in order to bring melt to the surface. You can see that most of the water starts off within the magma ocean. So water likes to be in the silicate melt, and it will partition partially into the atmosphere, and it is less happy within the solid material. Carbon dioxide, in contrast, much prefers to be in the atmosphere rather than in the silicate melt. So it has a different behavior during magma ocean evolution. The 2 different colors shown here are these are models for this particular exoplanet, GJ1132b, and the different colors are for different stellar radiation evolution models. So we have a high XUV evolution and a low XUV evolution in the pink. And so what's happening here is that in addition to having this partitioning between the 3 different reservoirs, there's also escape of the hydrogen from the system, which will ultimately lead to the cooling off of this magma ocean. So here we can look at how long the magma ocean can last for different abundances of water. Let me just bring this all up. So the magma ocean lifetime is strongly dependent on the bulk water abundance of the planet. So we're taking this planet and starting off with different initial water abundances. And again, there's these 2 different XUV evolution models. And so you can see that the high XUV model has much shorter magma ocean lifetimes than the low XUV model. And the reason for that is because of the figure shown on the left, the amount of water that is escaping from the planet. The high XUV is driving significantly more escape. So this is showing the fraction of water lost from the planet, again, as a function of the initial water abundance. So the blue model, the high XUV, is losing significantly more of its water, especially at these low water abundances, than the low XUV model. The water that is remaining in this low XUV model is actually trapped within the mantle. So there isn't a significant water reservoir on the surface of this planet at the end of these evolution models, but there remains a fair amount of water within the interior that could potentially be brought to the surface in later episodes of melting. So that brings me to these models of deep volatile cycles, where we're looking at the evolution of the planet after the magma ocean stage has ended. Now, what we need for these deep volatile cycles to operate is we need a way to get volatiles out of the mantle, and that occurs through volcanic outgassing. And then we need a way to get volatiles back into the mantle. For the volatile cycles on the Earth, we think this occurs primarily through subduction of oceanic plates and volatiles that are trapped within those plates. And this relies on the operation of plate tectonics. But not all planets, in fact, most other terrestrial planets, do not seem to have plate tectonics. They seem to be in sort of stagnant lid regimes, and I'll talk a little bit more about that. And it's not really clear if there is actually a way to get volatile recycling in a stagnant lid planet. there are a couple of suggestions that we can have sort of plate delamination, or we have material dripping off the bottom of a conductive lid, which might potentially, over longer timescales, lead to volatile recycling. So here's sort of schematic diagrams of this difference between plate tectonics versus stagnant lid. So this is the overall mantle convection style of the planet. We're all fairly familiar with plate tectonics. What is happening is we have a plate on the surface that will be subducted into the interior, and so this upper layer is actually participating in the full mantle convection of the planet. Up here we're seeing the sort of a schematic of the temperature structure in the planet. Again, we have the solidus and the liquidus as a function of pressure for the planet. And here we have a piece of material is coming up along an adiabat, and once it crosses the solidus, if it's part of an upwelling, it can start melting. So this gray region is where we would potentially have melt within the system. For the stagnant lid, on the other hand, we have this thick conductive lid that is not participating in the overall convection of the system. So what is happening in the temperature structure here, you can see, again, we have the solidus and liquidus, and the temperature profile through the lid is conductive. So as we're bringing our material up from the interior, it crosses the solidus here, but then it hits the conductive lid and it cools off very rapidly. So we get much less melting occurring in a stagnant lid sort of system. So we get less overall outgassing from the system and not much return of material back into the mantle. So let's talk a little bit more about how this would operate in the plate tectonic system for the Earth. This is looking again at the deep water cycle. So what's happening, we have our continent and we have our oceanic crust. And the crust contains sediments that have a significant amount of water and has some hydrated crust and hydrated mantle minerals. And as the crust is subducting, some amount of that material, particularly on the top of the slab, is going to start dehydrating and melting right away. And so you can get immediate melting in this arc region. And so we have arc volcanism here. So this is actually why we have the ring of fire around the Pacific Rim, as there's a lot of subduction going on around the Pacific. And so we get this arc volcanism in places like Japan. And the outgassing is coming mostly at mid-ocean ridges where ocean plate is being created. And so we have melt coming up from the deep mantle and is degassing and releasing water that was found within this melt. So this process over here, subduction, we'll call ingassing or regassing. So we can try to measure the fluxes of volatiles into and out of the mantle at the present day. This is work from Rita Parai. And what we're seeing here, so they're trying to use this constraint that the sea level on the Earth does not appear to have changed significantly over the last about 500 million years, based on sort of geological measurements. And they have found a value for the mantle output of water. And this is from looking at the rate of ocean floor creation. And you can estimate the amount of water that is being put into the surface through the creation of ocean crust. And so you get this sort of rate for water coming out of the mantle. And then if seafloor hasn't changed, then by necessity, the amount of material going back into the mantle must balance that rate. And so this gives an outgassing and ingassing rate at the present of about 2.5 times 10 to 11 kilograms per year. And that doesn't mean a lot to me or to really anybody. But in the absence of a return flux, this rate would means that it would take about 5.5 billion years to outgas one ocean mass of water at this rate. Okay, so in order to get the water that's on the surface today, it would take longer than the Earth's lifetime if it all started in the mantle to begin with, and if this rate were constant. But we think that plate tectonics was more vigorous in the past, so this rate cannot have been constant throughout the lifetime of the planet. Excuse me. So the deep water cycle, again, we can calculate this using a thermal model similar to the one we used for the magma ocean. So we're tracking the temperature of the mantle, and it is cooling off from some heat flux out of the surface, and heat is being created through radioactive decay. And heat flux is proportional to the amount of convection that the mantle is going through. So it's dependent on the Rayleigh number, which is dominated by the viscosity of the mantle. So this is where the dependence of the viscosity on water abundance is very important in understanding these deep water cycles. And then we couple this thermal model with a model for the amount of water exchange between the interior and the surface through ingassing and outgassing rates. Now, again, this temperature viscosity feedback is very important in these models. So we have water going into the mantle. This is the regassing rate, and it influences the viscosity of the mantle. If you're adding water into the system, that causes the viscosity to decrease. Remember that figure I showed you at the beginning. And if the viscosity is decreasing, that means that the mantle convection rate can increase. So it's more fluid, you can get faster convection. So that will lead to an increase in the heat flux out of the mantle. And so the temperature will drop. And as the temperature drops, that influences the viscosity of the system. Viscosity will increase now because you're cooling off the mantle. Now the convection of the system will slow down. You'll get less heat output, and eventually this feedback will lead to a balance between the heating rate in the interior and the loss of heat from the surface. Now the ingassing rates for these models depend on the amount of volatiles you're delivering into the mantle, and that depends on the amount of water that is in the crust that you're subducting. So this is a model for the various sediments and layers that are within a subducting slab. So we have sediments that contain a lot of water in the pore spaces, sheeted dikes and gabbros that contain a lot of hydrated minerals, and then some partially serpentinized lithospheric mantle. And so what we have here is there's a schematic here for the amount of water that's in these various layers in the subducting slab. And the other way you can look at this is the way I've done this in my own model is we take the temperature profile through the crust and compare that to the temperature of the stability of these various hydrated minerals. So this is the phase diagram for serpentine. And you can see that serpentine, as a function of pressure, is not stable above about 700 degrees C. So the way we do this in my model is we calculate the temperature profile through the oceanic slab, and everything at temperatures lower than 700 degrees C will be hydrated minerals. And so through this and through a quantification of the subduction rate, you can get the amount of water that is going into the mantle. And then we have applied this sort of model not just to the Earth, but looking at super Earths. And in this case, we need to look at what are the properties that are varying the most with pressure. So you can see that melting temperature and density of the mantle are not strong functions of the pressure within a planet. While thermal expansion and diffusivity are reasonably significant function of pressure, viscosity is by far the largest function of pressure. And so we looked at the effect that the pressure dependence of viscosity would have, and included also this water dependence of viscosity. And then we looked at how this water cycle would operate on planets of various sizes. So this is work from 2015, where what I was calculating, what I'm showing you here is the amount of water that is outgassed on a particular planet as a function of time for different planet masses. So this solid line is a planet the size of the Earth, and then this dashed line here is a 5 Earth mass planet. And there's, 2 and 3 in between. And so we have about half an ocean mass of water on the 1 Earth mass planet, and it's fairly stable over the lifetime of the planet. But you can see for the 5 Earth mass planet, it starts off with no water on the surface. And it's not until about 1 billion years in that it starts to get substantial water on the surface. So Nick Cowan and Dorian Abbott had another model for the water cycle, and they looked at the correlating the amount of water on the surface with ocean depth. And so we can convert this using this scaling to the surface area that's covered by water for these planets. And so for this 1 Earth mass planet, it's about 15%. And then for the larger planets, we get increasing surface coverage as the planet ages. Now, the more water we get on these planets, the less outgassing you might actually get. This is something that Ed Kite, I think, first mentioned in his 2009 paper. But what happens is that, again, we have this solidus and liquidus profile for the silicate melting. And for a normal planet that just has a relatively thin crust, we can have the base of the crust will be somewhere up here. And so the adiabatic profile, the melt is going to follow, comes up here. And so we get a significant amount of melting in this region between D and C. Now, if we have a significant amount of water on the surface, say we have an exoplanet that is a water world, that pushes the base of the crust to much higher pressures. And so we might get only a very tiny amount of melting. And if there's no melting, we can't outgas. The other problem with having too much water on your surface is that you might end up with ice at the base of your ocean. So this is also from Ed Kite's paper, where we're looking at the transition between water and high pressure ice phases. And it's not at, so this is at about half a GPa here, at about 250 Kelvin. So that's not very high pressure. You don't need a whole lot of water to start getting high pressure ice on these water-rich worlds. Tad Komacek and Dorian Abbott included this pressure-dependent outgassing, which was also included in Nick Cowan and Dorian Abbott's original paper, and combined that with this temperature-dependent ingassing rate from my model. And so what we're looking at here is the water mass fraction that you need for a planet to be considered a water world. So the original model is this orange pressure-dependent model. And then my model was this black line for temperature dependence of both ingassing and outgassing. And they're fairly similar. Again, sorry, this is as a function of planet mass. This hybrid model, on the other hand, has a much lower water mass fraction needed to turn these planets into water worlds. And that's where there's the planet is mostly covered with water, so there's a very small amount of exposed land surface on these planets, and that has implications for the potential habitability of these planets and the operation of the carbonate-silicate cycle. I'm going to skip this for time, unfortunately. So the carbonate-silicate cycle, as most people are familiar with, is we have CO2 in the atmosphere, and it reacts with water, and it will cause chemical weathering of silicates on the surface. And transport of those materials into the water can lead to formation of carbonates. And this has a climate feedback because this weathering reaction is dependent on temperature. And I'll just skip through this really quickly because I'm pretty much out of time. So we can see that the dependence of basaltic weathering on temperature is shown here empirically from measurements of basaltic fields. And then, but the chemical dissolution time for different minerals depends on their composition. So very mafic minerals like olivine have very short lifetimes, whereas the materials we find in the continental crust have very long lifetimes. So the rate of the carbonate-silicate cycle really depends on your crustal composition. Okay, and then just to show that the continental crustal growth rate is very uncertain, these are a bunch of models for continental crust growth as a function of time. So I'm going to skip over that last one and stop with my summary here. So the volatiles at the surface really control the climate, but there's a lot of volatiles in the mantle, and they affect the behavior of the overall system. The initial volatile abundances in the mantle will depend on the behavior of the magma ocean, so the solubilities of the volatiles, solid melt partitioning, and the magma ocean lifetime. And these deep volatile cycles really depend on the style of tectonics, and the carbonate-silicate weathering depends on the temperature and the composition of the crust. So with that, I'll stop there, and thank you.